Hello, champs. How are you? I hope you all are doing well. So, this is me, and I welcome you in lecture number 7 of Light. Let's begin this lecture without wasting our time. So, in this lecture, we will study about the image formation by concave lens. Yet, we have seen the image formation from the convex lens. Now it is turn to see the image formation in concave lens. So let's begin this class without wasting our time. So this is a concave lens. Now let's talk about the position of the object. So let's suppose this is your object and it has been placed at infinite distance from the lens. Now, position of the object is at infinite distance. Now, let's talk about the position of the image. So, to understand the position of the image, we have to take help of the ray diagram, which we saw in the previous lectures. So, this is a ray coming parallel to the principal axis. So because this is a concave lens, this will diverge the ray. Why will this diverge ray? Because this is a diverging lens. Diverging lens. That's why it will diverge the rays. Now, if you want these rays to meet at a point, then this is not going to happen. Why? Because these rays are going in different direction. You can see this is a ray. After the divergence, it is going here, and this is again a ray, and this is coming parallel to the principal axis. After the refraction, it is going in this direction. So because they are in different direction, one is here, another one is here, so they are not going to meet at any point. So what you have to do, if you want to make it meet, then you have to increase it in this opposite direction. So at this point, they will definitely appear to be meeting. So the same thing I will do here. I will increase it here like this. And I will also increase another ray like this. So at this point F1, these rays appear to be meeting. These rays appear to be coming at this point. So that's why we would say that our image will form at F1. At F1. So the position of the image is at F1. Now, let's talk about the size. So as you can see in this picture, the size is very, very small. So you can say the size is highly diminished. Highly diminished, or you can call it point size. I hope you got my point. Now let's talk about the nature of the image. So to understand the nature of the image, I do not need to explain you again and again the same thing, because I told you many times that these type of images where rays are not actually meeting are known as virtual images. And we also know that virtual images are always erect. So it means the nature of this image is virtual and erect. I hope you got me. Now, this is the first case in concave lens. Now, let's move on to the next slide and let's see what's there. Okay, so this is the second case. This is the second case. So in this case, what will we do? We will simply place this object anywhere between the optical center and between the optical center and infinite. Because in case number first, we had placed the object at infinite. Infinite means very, very far from the lens. But here we can place it anywhere. So now let's see what happens. This is a ray coming parallel to this principal axis, and whenever a ray from a concave lens, whenever a ray coming parallel to the principal axis, it always appears to be passing this focus f1. Now this is another ray. This is passing through the optical center and it will pass without any divergence. So this is a point where these rays appears to be meeting. So we would say that a image will form at this point. Okay. So let's talk about position of the object. So anywhere between infinite and O, which is optical center. Now let's talk about the position of the image. The position of the image is between f1 and optical center. And you can see in both the cases of concave lens, the image is the same side of the lens. Or you can say the image is at the same side of the object. Now let's talk about the size. So you can see that the size here is very small. The size here is small. So for small sizes, we write diminished. Let's talk about nature. So nature of this image is virtual and erect. Why this is virtual? Because rays are not meeting here. And this is also erect. This is an upright image. That's why it is erect. So I hope guys, you might have been able to understand this second case of the image formation by concave lens. So here we don't need to discuss more cases because there are only two cases in the case of concave lens. But when we talk about convex lens, then there we had to study six cases in convex lens. But here we just have two cases, so it is easy to remember. Now let's move on to the next slide. Okay, so here in this slide, I have just cut it short, cut the rules short, so that you can easily understand and easily memorize before appearing in exam. So this is, let me change pen. Okay, so this is the first case where the position of the object is at infinity. So when we saw first case, we had also seen that the position of the image in that case is on the first focus f1. Focus f1 means the first focus because there are two focuses in the case of lenses. Now let's talk about the size. So the image size is point size. It means point image. Let's talk about the nature. So concave lens always forms virtual and erect images. Virtual and erect images. Just like convex lens. Convex mirror. Let me erase it from here. In the case of convex mirror also, we had seen that convex mirror was forming virtual and erect images. So now, let's talk about the second case. In second case, we had placed the object anywhere between optical center and infinity. So the position of the image in this case between optical center and focus f1. So in this case, the size of the image is very small You can see the size of the image is very, very small. And the nature of the image is again virtual and erect. Okay. So concave lens and convex mirrors always forms. Let me write it here for you. Concave lens and convex mirror always form virtual and erect images. So I hope guys you got my point. Now let's move on to the next slide and let's see what is there for us. Okay. So here the lenses are over. Okay. There are lots of examples, lots of things we have to study after that. But the lenses are over here. Now let's talk about sign convention of lenses. Now the numerical part is coming. We will be discussing lots of numericals. So to solve those numericals, we should have a basic understanding of sign convention of lenses. Although we had seen this sign convention even in the case of mirrors. So we don't need to put lots of efforts to understand these sign conventions because we had already seen this when we were discussing mirrors. So let me give you a quick idea what is sign convention. So the distances which are at right side of the lens, the distances which are at right sides of the lens are taken positive. Okay, it can be either mirror, it will work for both mirror or lens. So okay, let me again write it for you. Okay, let's highlight it also that we can use it in both the cases, in the case of mirror and lens. So the distances which are at right side are taken positive, distances which are left side are taken negative, and the distances which are upside of this axis are taken positive, and the distances which are below this line are taken negative. So this is just like a graph. When we see a graph, let's suppose this is a graph, this is x axis, this is y axis, this is minus y axis, and then this is x axis. So the distances this side are taken negative, this side also are taken negative, but here when I talk about right side of x axis, then the distances are positive, and here when I talk about the upside distances from this axis are taken positive. So the same thing you can easily relate from this diagram. Now, let's move on to the next slide and let's try to understand the lens formula and magnification. So this is a lens formula. So this is our lens formula. 1 by V minus 1 by U is equals to 1 by F. So what is V here? V is the image distance. The image distance. And U is object distance. U is what? Object distance. Now, what is M? M is magnification. And there is a formula for calculating magnification, and that is H dash upon H or V upon U. Now you might be confused what is H dash? Then H dash is nothing but the height of the image. And what is H? H is nothing but height of the object. So I hope guys you got it because we also saw this when we were discussing mirrors, but you have to be careful at a point because that is very, very, very important. Okay, let me mark star here. It is very important. Now, why it is important? Because when we were discussing mirror, then we write formula like this. Now you can be confused here because here I am writing minus before 1 upon u, but here I am writing plus before 1 upon u. So this is the difference between the mirror formula and the lens formula. So you have to be a little bit attentive here. Now let's move on to the next slide and let's talk about magnification again. So how do we calculate magnification? As we saw, magnification is nothing but h dash upon h. So the same thing I am written here, height of the object, height of the image by height of the object. So h upon h dash. Okay. Here you can basically this is written inversely. So h dash here and h here. So it will be like this, h dash upon h. Now magnification is produced by a lens, and a lens is also related to the object distance. So guys, I hope you might have been able to understand how do we calculate magnification. But there is other formula also which we haven't seen in the previous slide, that is V upon U. So after understanding this, let's move on to the next slide. And here we are. Okay. So here what we will be doing, we will actually solving a question. We will actually solve a question. So what is this question about? Okay, so before going to the solution, let's talk about the question. So a concave lens, don't be confused here, this is question number first. So a concave lens has focal length of 15 centimeter. Okay, so what has been given? The focal length, and that is 15 centimeter. Now I'm talking about the concave lens. I'm talking about the concave lens. And what is the focal length of a concave lens? I mean to say that it is minus 15 or plus 15. Then definitely it is minus 15 because the focus of a concave lens is negative. Now, at what distance should the object from the lens be placed so that it forms an image at 10 centimeter? Now, other thing we have given, let me write it here for you. We have been given. Okay, so this is the data which we have been given. Focal length, and he also gave us the image distance, and that is 10 centimeter. Now, if I ask you that should I take it negative or positive, then definitely it will come in negative. Why? Because you might have seen that when we were discussing concave lens, then we saw that concave lens always forms an image at left side, at this side. So that's why it is taken as negative, so minus 10 centimeter. Now, also find the magnification. So the question is asking the object distance because it is saying at what distance should the object from the lens be placed, because here we have been given the image distance. Now it is indirectly asking us the object distance. And the other thing is also asked, and that is magnification. So first of all, let's calculate the object distance. So we will use the lens formula. Okay, and what is the lens formula? 1 upon V minus 1 upon U is equals to 1 upon F. Okay, so let me write it here for you. The value of V is minus 1 upon 10. The value of U is to be calculated. The value of F is minus 1 upon 15. So let me take it here. Let me bring it this side. Let me send it this side. Okay, so if I take the LCM, then it will give me 33 plus 2 and 5 upon 30. It will give me 6. So the object distance is 6 centimeter. Okay, what is the object distance? This is 6 centimeter. So if you place a object at 6 centimeter from the mirror, then its image will be at 15 centimeter. Okay guys, I hope you got my point. Now let's talk about the magnification. So magnification is very simple. The formula of magnification is V upon U. So what is the image distance? The image distance here is 15. Sorry, 10. Okay, and what is the object distance? Is 6. Okay, I hope you got me. Okay, guys. So here we have done a little mistake. So let's find out what mistake we have done. Okay. So here we forget to add minus sign. Okay, we forget to add minus sign. So let's again do it. Let me erase it from here. Okay, this has been erased. Let me erase this also. Okay, so now let's take LCM. This will give us 30 and 3 times. This will go 2 times 1 upon U. And if you solve it, then the value of U will be, okay, let me solve, minus 1 upon 30. The value of U will be minus 30. Okay, so this is the right value. Do you know how did I find this mistake? Because when I find out the magnification was higher than 1. The magnification was higher than 1. But in the case of concave lens, the magnification always come less than 1. Okay, because the height of the object is always greater than the height of the image. Okay, so that's why I found out the mistake, because the value of m was greater than 1. So it was wrong. So now let's find out the value of m. M is equals to V upon U. And what is V? What is V? Where is V? Okay, minus 10. And what is U? U is minus 30. So it will come 1 by third. So value of m is 1 by third. So we have calculated the magnification and we have also calculated the object distance. I hope guys you got it. Now let's move on to the next slide. Okay guys, so here in this slide we will solve a question. So in this question, what has been asked, a convex lens forms a real and inverted image of a needle at a distance of 50 centimeter from it. Where is the needle placed in front of the convex lens if the image is equal to the size of the object? Also find out the power of lens. So first of all, let's see what data have been given. So been given we have been given that the image distance is 15 centimeters, because you know that a convex lens is making real and inverted image. So convex lens always makes real and inverted image on the right side. Okay, because we have seen till fifth cases the image was being formed at right side. But in case number 6, the image was formed left side. Okay, So because it is real and inverted image, that's why it will be formed right side. Okay, had it been the virtual and erect image, then it would have been sixth case, and in sixth case we saw that the image was formed at left side. So because it is at right side, that's why we will take it positive. Because this is at right side, that's why we will take it positive. Now, where is the needle placed in front of the convex lens if the image is equal to the size of the object? So the other hint is given that m is equals to 1. Now you might be thinking that why I write it 1, because I know that value of m is equal to h dash upon h, and here it is given that the image is equal to the size of the object. So it simply means that a value of h dash and h is equal. That's why it will cancel out and give us the result 1. Now I have to add minus here. Why do I have to add minus? Because the image formed here is a real and inverted image. And real and inverted image, for real and inverted image, the magnification always negative. Okay. Now let's talk about the things which we have been asked. So first we have been asked that you have to calculate the power of lens. Okay. Now what is power of lens? Let me tell you. It is very simple. I will explain you later parts. But for now, we just need to understand that there is a formula to calculate the power of lens, and that is P is equals to 1 by F, where F is taken in meters. F is taken in meters. Okay. And the other thing is asked object distance. Object distance. This is the second thing which we have been asked. Object distance. So first of all, let's try to calculate the object distance. So how to calculate the object distance? We have given m, and that is minus 1. So m has a formula that m is equals to v upon u. So I will just simply write it here, v upon u, and we know that value of u will become minus v, and v is 50. So that's why u will become minus 50 centimeter. So this is our first answer. This is our first answer. Let me highlight it for you. Okay. Now, what other things have been asked? We also have been asked the power. So to calculate the power of the lens, we have to calculate the focal length. And how to calculate the focal length? We will simply apply the lens formula. Okay, so what is lens formula? The lens formula is 1 by V minus 1 upon U is equals to 1 upon F. Now what is 1 upon V? V is given 15. And what is U? U is given what? U is given also 50. Okay, V is 50 and U is also 50, but it is in negative sign. It is with negative sign. So when I put it here with negative sign, it will become positive, and this will give you 1 by F. Now if you calculate it and solve this, then you will get the value of F will be 25 centimeter. Now why it is 25 centimeter? Why it is not in meter? Because the values which we have put in the formula was also in centimeter. So here we got a focal length. Now you have to calculate the power. So for power, you will simply put this value, but you cannot directly put it because here the values are put in meter. Okay, so this is not in meter, this is in centimeter. So first of all, you have to convert it into meter. So what you have to do to convert it into meter? Just to divide it by 100. So you will get 0.25 meter. So now you have to put 0.25 meter here, and when you solve it, then you will get 4 diopter. The unit of power is diopter. The unit of power is diopter. We will learn these later parts. So guys, I hope you got my point. Now let's move on to the next slide. Let's try to understand what is there for us. So here, okay, so here we are. This is a next slide. So in this slide, we have to discuss the power of a lens, which I had told you when we were solving the last or the previous numerical. So the power of a lens is nothing but the reciprocal of focal length. But one thing is to be remembered, and focal length will always be in meter. If it is not in meter, then first you have to convert it and then put it in this formula. Now let's move on to the next slide and let's try to understand. Optician prescribe corrective lenses indicating their power. Let us say the lens prescribed has power equal to 2 diopter. This means the lens prescribed is convex. The focal length of the lens is 0.50 meter. Similarly, a lens of power 2.5 diopter has a focal length of minus 40 meter. The lens is concave. So basically, it is it has been told in these lines that if you have given power, then you can calculate focal length. How can you do that? It is very simple. We know the formula of power is 1 by f. So if you cross multiply it here, then you can also write it 1 upon p. So if you have power, then you can also calculate the focal length. So power is given 2 here. So in this case, the focal length will become 0.50, and remember it will come in meters because when we calculated power, then we put the value in meters. Okay, so that's why the focal length will also come in meters. And the same thing happens here. The length of power 2.5 diopter has a focal length of minus 0.50 meter. And here the lens is concave because the focal length is minus is in negative, so that's why the lens is concave lens. So I hope guys you got my point. Okay, so before moving ahead, I want you to answer a question. I am asking you a question, that this is a focal length of which mirror? This is a focal length of which mirror? Convex or concave? So give me answer very fast. Okay, so this has been given in positive. Okay, this is a positive focal length. Now remember, when we were discussing convex mirror, then in the case of convex mirror, the focal length used to be positive. So that's why this focal length is that of convex mirror. Now let's talk about this case. If I have if I have given you the focal length like this, minus 40 meter. Now you tell me which type of lens it is, then it will automatically become concave lens because the focal length here in this case is minus 40. It is coming in minus. So I hope guys you got it. Now let's move on to the next slide. Many optical instruments consist of a number of lenses. They are combined to increase the magnification and sharpness the image. The net power of the lenses placed in contact is given by the algebraic sum of the individual's power P1, P2, P3 as P is equals to P1 plus P2 plus P3. So what has been written here, let me explain. For an example, you have a lens of power 2 diopter, and on the other hand, you have also a lens of power 3 diopter, and you have also a lens of power minus 1 diopter. Now you have to calculate the overall power. If you combine these lenses, then what is the overall power? Then you don't need to do a lot of things. You just do the algebraic sum. You just have to do the algebraic sum of these quantities. So let's suppose this is 2, this is 3, this is minus 1. So the answer would be 4 diopter. So this is the net power. This is the net power. Okay. I hope guys you got my point. Now let's see the other thing. Find out the power of a concave lens of 15 meter. There are some questions given. So we will just calculate that the power of a concave lens where we have been given a focal length. Find out the power of a concave lens of 15 meter, and 15 meter is focal length. 15 meter is focal length. Okay, so this is 15 meter, and because this is a concave lens, then the focal length will become negative, because a concave lens always have a negative focal length. So now if you have to calculate power, then you will simply just because it is in meter, so you don't need to convert it in meter because it is already in meter. So just put this value in this formula, P upon 1 upon F. P is equals to 1 upon F. So P is equals to 1 upon minus 15 diopter, because it is power. So the value of P will minus 1 upon 15 diopter. Now let's talk about define 1 diopter of power of a lens. So basically we know that the formula to calculate power is 1 upon F. Now we have given the power 1 diopter. Our power is already 1 diopter. So now you tell me, when will the power is 1 diopter? When this value is 1, okay, when the focal length is 1. So what can we say? That 1 diopter is a power of a lens having 1 meter focal length. 1 meter focal length. Okay, and because this focal length is positive, so that's why it is the power of a convex lens. It is the power of a convex lens. I hope guys you got my point. Okay, so here I am ending this lecture. I hope you have been able to understand whatever I told you. So see you in the next lectures. Bye bye.